Okay, this will be lesson 5 of chapter 8, the final lesson in this chapter. And here we're going to talk about, we'll do some math with the idea of covalent bonds. So we'll talk about the strengths of covalent bonds. And essentially the idea is a measure of how strong is the bond, say between two chlorine atoms. The Cl2 molecule has a bond between them, and we're asking for the strength of this bond. And the strength will be given again in kilojoules as a measure essentially of how much energy it takes to break that bond. We'll call this bond enthalpy, signifying it with D, and this will actually be related very closely to our discussion in chapter 5 of delta H, because remember the heat change for a chemical process takes into account the relationship between reactants and products and the formation of products from reactants. In essence, what's happening as we calculate delta H is bonds are being broken, new bonds are being made. So we can connect this to delta H by measuring the strength of each bond that's going to be broken, that's going to be made. And here the statement that the greater the bond enthalpy, the stronger the bond, which makes sense. Essentially we're saying that the stronger the bond, the more energy it takes to break that bond. So what we can do is we can actually show this by drawing, say, by writing a little reaction. So here we have CH4 breaking apart into its elements, which means since the CH4 molecule had 4 equivalent carbon-hydrogen bonds, we essentially must break each one of these. So as we break each one of these, it takes 1660 kilojoules to do so. Because there are 4 equivalent bonds, what we could do is we could divide this by 4, and that's exactly what we're doing here. We're taking a quarter of it, giving each bond having an enthalpy of 415 kilojoules. This essentially is 60 divided by 4, giving us 415 kilojoules. So the carbon-hydrogen bond has this much energy between it. It takes this much energy to break the carbon-hydrogen bond. Now we can list all these bond enthalpies, and these have been tabulated and figured out. For example, here is the carbon-hydrogen bond we've been talking about. It's 413, slightly lower than what we calculated. It turns out the numbers won't be exact, depending on really how you arrive at these numbers, but they'd be very close, and we can actually use these numbers to predict to a very good degree how much heat the whole reaction will release, is the idea. So these are all in this table, table 8.4. Feel free to refer to it. A quick idea I want to show you here is, first of all, the difference between single bonds. All these up here are single bonds, and double bonds, which are here, and triple bonds are here as well. What you'll see in general is that multiple bonds, doubles or triples, have a higher bond enthalpy than single bonds. In fact, take a look at the carbon-carbon single bond of 348 kilojoules, the carbon-carbon double bond almost twice that, and the triple bond even higher. So this is a general trend. Secondly, if you take a look at this region right here, and what you're seeing is bonding to chlorine, bromine, iodine. Well, think of just actually go up a little bit. Why don't we do take a look at this section right here. We essentially are going down the periodic table on the halogens. So we have fluorine, down goes to chlorine, bromine, and iodine. And as you see, the enthalpy is actually decreasing. And the idea here is each one of these gets successively bigger and bigger. So the iodine atom, for example, is bigger, we'll say, than the bromine atom, which is bigger than the chlorine, which is bigger than the fluorine. So when the carbon bonds with it, essentially the carbon bond is now further between the two, and this creates a longer bond, therefore a weaker bond. So that you can actually trace this and see a lot of these types of patterns throughout. But in general, the idea here is that triple bonds and double bonds are stronger than single bonds, and the single bonds also vary between themselves in strength. So here's how we are going to connect this to the reaction, to the enthalpy of reaction, really the delta H that we talked about in chapter 5. We can calculate the amount of energy that it takes to break bonds. So we take the broken bonds, the energy of the broken bonds, minus the formed bonds, the bonds formed. recall, if you want to break a bond, you must put energy in. That makes sense. And when you make a bond, energy is released. The molecule, in a sense, thanks you by releasing some energy. So what we could do, remember, if you want to put energy in, that is endothermic, that's a positive value. The delta H is positive. And then if energy is released, the delta H is actually negative. So there's an equation that says the heat of reaction is the summation of the broken bonds minus the summation of the formed bonds. Well, since formed bonds release energy whenever bonds are formed, that's when you get this negative, and that's why we subtract this number, and broken bonds require energy input. That's why this number is positive. So essentially we have ourselves, this is a positive value, this is a negative value, and we just combine the two. So you can look at it logically, or you can use this equation. I will encourage you to think about this more logically, but the equation does not hurt. So here's an example of what we can be asked to do using this information. We have ourselves the task of calculating the enthalpy of the whole reaction for the following equation. We have iodine breaking apart, or iodine recombining with chlorine to form ICl3, iodine trichloride. And here we've listed, essentially from that table, we've pulled some bond enthalpies. There are three types of bonds that we'll be dealing with in this example. So the way to do this is to count how many bonds we're breaking and how many bonds we're forming, and then combine the two. So it looks like we're going to, let's rewrite the equation here. We have I2 plus 3Cl2 giving us 2 ICl3. And in order for us to calculate how much we're breaking and how much we're making, why don't we just redraw these using the Reuleaux structure. So the iodine, I2, actually looks very simply like so. I'm going to omit the electrons around the outside for clarity. Then we have 3 chlorine molecules, each with an equivalent Cl-Cl bond. And then in the product, we have 2 ICl3 molecules. And here they are. So what we see essentially is that we are breaking an I bond. That bond from the previous slide is 149 kilojoules. Since we're breaking it, this will be a positive value. We have to break 3 of these Cl-Cl bonds. From the previous slide, that's 239 kilojoules. And it's also going to be positive, but because there's 3 of them, we must do this thrice. So we get ourselves, what is this here? 27, 9, 10, 11, 6, 7, 717 in this case. And then we are making, let's count them. We're making 1, 2, 3, 4, 5, 6. We are making 6 ICl bonds. So from the previous slide, if you take a look, ICl has a bond enthalpy of 208. So if we have 6 of these, essentially if we multiply 6 by 208, grab your calculator for ease of computation, and you get yourself 1,248 kilojoules. Now this value will be negative because we are actually making these bonds. Anytime you make bonds, heat is released. So then let's go ahead and do a total accounting. So the total in our case will be 149 plus 717 minus 1,248. This is a strange way of putting it, but for a total of negative 382 kilojoules. And this essentially is our delta H. So notice we were able to obtain a delta H value just by counting each individual bond. And this is actually easily done, and when we run this reaction, we will see that the change in heat is very close to which was calculated here. It's not a perfect match, but it's actually pretty close, and close enough for us to be able to use this method of verification. And then a quick discussion here about, we sort of mentioned this just on one of the previous slides, but the idea is that multiple bonds are actually shorter than single bonds and stronger than single bonds. This makes sense because a multiple bond essentially forms a stronger attraction, say, between the two atoms, pulling them closer together to one another. And the analogy is actually with rubber bands. If you wrap 3 rubber bands around 2 objects, it'll bring the objects closer together than if you wrap just one. And then it is harder to break 3 rubber bands than it is to break 1. So that analogy is actually pretty fitting in this regard. So you can see 3, so if we take a look at 3 carbon bonds, a single, a double, and a triple, you'll see that their length decreases, which means the atoms are getting closer and closer and closer. And you'll see that their bond enthalpies, as we've seen for the previous in the previous slide, would get higher and higher and higher. It is tougher to break a triple bond than it is to break a double and a single bond, is the idea. So this trend is actually everywhere. You'll notice with nitrogens, this trend is also followed. Really, in any case, this trend is followed. Okay, we're going to finish talking about some metallic bonds. So we've mentioned metals in the previous chapter, but metals by definition conduct electricity, heat and electricity. This is very important. Metals are conductors. They're malleable, so you're able to shape them and form them into sheets. So they're deformable. Think you can deform these. For the same reason they're ductile. You can actually string them into wire. In fact, a wire here is copper wire, copper rods which are strung into copper wire. This is actually gold leaf, very famous. The ancients used to cover many of their monuments or statues or little figurines with gold foil, because gold is so easily shaped. Very easy to get a very, very thin layer of gold around something. And the idea here is the reason this happens, this deformation is allowed, is because the atoms are packed. However, they can slip past each other. And this is also why the metals are not brittle. In fact, if you apply a hammer to a metal, it will not break into small chunks. It'll just simply deform. Most other solids, ionic solids, non-metal solids, are actually brittle. So if you try to do the same thing to, say, even silicon, which is a semi-metal, silicon will actually break apart into little tiny pieces. So if you have a big cylinder of silicon and you apply a hammer to it, it'll actually break apart into little small chunks. You'll actually get yourself a nice mess on your hands. And the reason these properties are seen in metals is because we describe the bonding in metals as a sea of valence electrons. And it is cations, essentially, swimming in a sea of valence electrons. And the idea is these valence electrons are not permanently attached to any single atom, but they are free to move around. They're weakly attracted. And that's why metals can easily conduct electricity. You can pass an electric current through metals, and it's able to be passed on through the metal. So the attraction holds the electrons, but not tight enough to impede their flow, is kind of the idea. And this is why, then, metals are conductive, and why they are able to get deformed. This model essentially explains these properties. Another word about metals. Metals can form a very interesting variety of substances called alloys. Now these alloys essentially are a combination of different metals or different elements put together. You don't necessarily have to have two metals. You can have a metal and a non-metal, and the famous case of this is actually steel. Steel, if you're aware, famously is iron with carbon, a little bit of carbon. You don't have to necessarily have two metals in order for this to happen, but these are actually not considered to be compounds. Compounds, if you recall, have a definite formula to them. So for example, if you have yourself calcium chloride, you literally have one calcium for two chlorines. And that's your ratio. That's a fixed ratio. With alloys, the ratio can be anything you want. You can have 1 to 5, 2 to 6, 1 to 500 atoms. So because the ratios are not set, these are not called compounds. These are called homogeneous mixtures. So that's actually a very important difference between alloys and compounds. Alloys are not compounds. So what you see here, a very famous alloy is brass, depicted here. And brass is a combination of copper and zinc. And brass is actually very important, and many of our common metals are actually made of brass. Here, this is actually steel, most likely. And this is something called white gold. Very often, white gold incorporates silver into gold, oftentimes platinum, sometimes palladium, other precious metals, along with gold, to give you this silver color and to give it some strength, is the idea. And if you take a look at the picture here, there's a picture or two for your visual pleasure, and you can discuss, for example, the two types of alloys. These are called substitutional alloys, where another atom substitutes for the original metal, or interstitial alloys, where you have the tiny atom in the middle between the metals. So this is just a little detail. But alloys are not only important to our industry, but also very interesting and fun to work with, as you'll see in the next slide. And a famous alloy that's very interesting and fun is something called memory metal. It's made of nickel and titanium in a certain ratio. And interestingly, this metal can be deformed by changing temperature. Temperature can actually change the arrangement of the metal. Hopefully you had the pleasure of seeing a demonstration of this in Chemistry 1. But you can actually deform the metal and make it into a certain shape, and then by increasing the temperature, you can get it back to its original shape. So you can set the shape. So here, for example, the piece of metal is shaped to spell the word ice, and then somebody had deformed it, but as you put it into the hot water, the ice configuration returns. Very interesting. Allows us to play around with these ideas. These are actually used in some applications in the real world. And I thought I'd leave you with my favorite alloy, and that is NaC, sodium-potassium alloy. We know that both sodium and potassium are metals. However, they're very reactive metals, but you could make an alloy out of them, and this alloy is a liquid, much like the mercury being a liquid. However, if you take a look, if you've ever seen pictures of mercury, mercury actually beads up, makes into these kind of beads that do not adhere to the surface. But NaC, sodium-potassium alloy, actually adheres to the surface. So you can see how it actually has an attraction for the surface. So it looks quite a bit different, but it looks very neat. And it's used oftentimes as a scavenger, essentially for any traces amount of water or something in some sort of vessel. But NaC is, we'll finish up with good old NaC. And that completes Chapter 8.